happy to introduce Professor Tang, Tang. She's an eminence in the haptic industry and research. She has many contributions in both academia and industry. Let her give or say a few words about herself. She's currently working at Google and also Nesh, Senior Human Factors Engineer, responsible for some of the latest progress in haptics implementations in Windows, not just a specific device, but entire platform, which is something that we've been looking for as industries, people that been watching the development of haptics. And myself, a little bit of me before I transfer it to you, Hong and Nesh. I'm the head of the Human Machine Interface Lab. We deal with everything that has technologies that communicate with the user. As simple as that. I'll delve a little bit more in the next slides. And I've been around also for a long time doing innovation in industry and on haptics. Hong, can you tell us a bit about yourself?
Hey, thanks, Manuel and Miguel, for the introduction. So I come from an academic background, but throughout my academic career, I've been doing extensive consulting, very interested in solving problems out there in industry, and finally got a chance to first do a 4-year stint at Microsoft Research, and now working full-time at Google, actually developing haptics Pixel phones, and also enjoy haptics APIs. Nesh?
Thanks, Hong and Manuel. Hi, everyone. My name is Nesh Gande. I'm a human factors engineer at Microsoft, but my focus is on designing input and interactions as part of the Windows platform and how it shows up on devices. Now Xbox is also built on Windows, so it extends to gaming as well. And my passion is really to take our visually dominant interfaces and, interactions that have been around for a while and really evolve them into, 2026 and beyond with more rich and multimodal interactions.
Perfect. Thank you, Nesh and Hong, for that. So let me start with what is HMI and why are we doing this, right? So HMIs, I want to talk about this. So any human interaction that we have with a device usually starts with the intention of a user communicating something with the device. And there is a goal. Usually, when we're trying to interact with a trackpad, a button, we want to do something. We want to exert an action and a reaction from this device. And these inputs are usually transferred or captured through the device using touch, voice, gestures, through the sensors that are embedded in that device. And this input is then transferred and processed inside the device to exert a change in the state of the machine that we're interacting with. And this is usually processed by a computer program, hardware, or any other device that we have seen in commercial applications. But this interaction is not complete until the system changes that state or reacts to us. And that's the feedback that we are always looking for. When the system receives that input, whether it's visual, audio, or haptic, and reacts to that. But more importantly, to touch, we can actually receive that information. And touch is the only sense that we have that can be truly interactive. We can exert information or give information to the computer, and at the same time receive that information. That's the haptic or the feedback loop that we always engage with these devices. After that, we have a communication that has been established with the device, and that's when the perceptual part of this happens, because we're interpreting something, the device is doing something, we're interpreting what happens at that time or what the state of the device is going to be in the future. What I'm trying to get at with this one is that traditionally the interfaces were dominant in audio and voice, but haptics also belongs in this feedback loop. And traditionally we use only click interfaces, but click interfaces are limited. And one of the things that Hong Tan is going to show you today is that touch actually can interpret much more than one single bit of information or a click. At Bolera and Innovobot, this is where we see how to implement this type of interfaces. We don't think haptic feedback or an HMI is only one single layer, or the actuator or the haptic signal, we see this as a complete divide. I see not only for HMI systems that we do this. We look at the system as an entire solution with many layers that need to be intertwined and carefully crafted in order to provide a solution. Anything from the user perception, what is exactly that we want to give to your user, what software we need to implement in order to process that information, the lower layer, which is the firmware, the embedded system that we need to create and program in order to control the hardware, the actuator, the sensors, that ultimately are going to provide the signal to the user in form of haptic sensations. The other layer that we promote extensively and are proponents of is the testing and validation, because if we create something, we need to make sure that that device is consistent, not just across devices, but across users. So we need to translate that perceptual intent that we have at the higher level into engineering units that we can test and measure to ensure that the device is actually doing what we are doing, or what is intended to be doing. And currently, haptics is at an inflection point, right? That's the reason why we think haptics matters more now than in the past. And for many years, the dominant examples were relatively simple: phone vibration, basic click, and a single actuator. But more and more, the market is moving towards richer haptic feedback with multi-actuators, spatial haptics, wearables, excuse me, and other type of interfaces that provide richer haptic communication. There are also other drivers, like I have in my fourth point there, this AI personalized UX, tactile standards, and surging demand for multiple consumer electronics that require stringent QA systems in order to make sure that they are consistent across the line. So this is not only a research topic anymore, it used to be, it's becoming a product and a platform topic. From this perspective, Nesh, does this match what you're seeing in the PC ecosystem? Is haptics becoming more than a premium hardware feature?
Well, that's a great question, Manuel. I think at least, for the duration that I've been in this industry, like a lot of the haptics development has been focused on like emerging technologies, new ways of actuating, new ways of providing rich feedback, which has been really awesome to see. I think especially like with the wave of mixed reality and virtual reality development we had in the early 2020s and like late 2010s. I really thought that this was a very emerging field, lots of new developments happening, but where I felt that it was lacking is really like having these experiences scale to a lot of people that are using them. Probably the most prominent example is in automotive or in mobile, where really simple haptic systems were in place and were really useful, and to the point where people didn't even know that they were interacting with an active haptic system, but they were. And so now I feel like in this next era, what really I think is, what my goal has been is to bring these haptic systems to the more people and have it be useful, because the technology is going to keep advancing, but really for me, I think it's the impact that happens when the experiences actually reach the people in their everyday lives and their workflows and actually helps them. So I think that's kind of, to answer your question, that's where I think that's why now we're at an inflection point where we're starting to see these experiences scale to different devices and platforms.
Thank you, Nesh. Let me see. Moving on. So this slide tries to capture the thesis of this presentation. We have seen currently that we are limited to very simple interactions in commercial devices, but what Hong is going to show us in her part of the presentation is how touch can be used for much more than a single interaction or single haptic effect interpretation. From there, we're going to move into what a platform can do in order to implement those type of languages or rich communication systems. And at the end, I'm going to come back to show how we can implement that as part of a product or an HMI system. As I have it here in my slide, the question is not necessarily how to add a vibration. That's probably well known by now, but the question is what should the user feel and why? So with that, I pass it on to you, Hong, for your presentation on perception-based haptics.
Great. So in the next few slides, what I'm trying to show is that touch is capable of processing a lot more information than any product utilizes it for. So I want to give you two examples. One is a natural example, as in occurring in a sort of field, and this is a communication method called a tadoma. So on top of the slide, I showed that a click is 1 bit, right? You have two states, on or off, whereas tadoma can carry, and I'll explain what that means in a second. It can carry 12 bits per second, meaning 2 to the 12th power of number of symbols communicated within a second. So that's day and night, right? So Tadoma stands for Tad and Omer. These are the two children who were first taught this touch-based communication method in the US. In this photo you're seeing in the middle is my dear late advisor, Nat Durlak. He's having a conversation with two gentlemen who are both deaf and blind. The way they do the communication is they place their hand on the speaker's face, and they usually put the thumb across the lips and the other fingers fan across the cheek. With that, they can monitor the mechanical actions associated with the articulation process. And through that, with the palm of their hand alone, they can understand natural speech. And I want to emphasize that because when I met the gentleman on the left, he just put his hand on my face and it's like, oh, hi, how are you? And I'm like, oh, Mr. Leonard. He's like, oh, where are you from? I'm like, what do you mean? He's like, you have a foreign accent. So they pick up not only speech, they pick up all the additional nuances that, just when we have oral communication can say you're a New Yorker versus somebody else, right? So I want to show you a precious video. On the left is the experimental.
Do you like to go to the movies?
Is a deaf and blind individual. But since we're very scientific, we make sure he cannot see or hear. So the deaf and blind subjects wearing, eye shades and a headset. What he's doing is he's repeating back what he's feeling through his hands, through his speech. So Manuel, if you could just play a bit more of audio.
The volume?
Yeah.
But not only that. They wanted work in many trades.
They wanted work in many trades
and professions.
Okay, I'll talk a bit more over this. So this is called tracking. It's another way of testing speech reception. So the point is that with the palm of their hand, they can process a lot of information. But can we do this in devices? So if we move on to the next slide, this just kind of visualizes the signal you feel. Each white dot is a vibrator on your arm, and the signal kind of moves around.
Okay. Move. So. Okay. So. Row.
And we designed patterns specific for the 39 phonemes of English, 25 consonants and 14 vowels. And each one is unique. We train people on feeling them, and then he sounds it out. So if he feels ma-oos, he's like, it's moose. So it's a phoneme-based tactile communication sleeve. We call it TAPS.
In the past, we have been or in general for wearables and systems that you can wear or touch that have multiple dimensions. You can design this type of languages, and certainly we have done so in the past for some companies in which you teach them to learn something, right, to tactile feedback. So I can see clearly the applications that we can derive from these discoveries or this work that you have done in the past.
That was a question that came in from Marina just now in the chat room. What could be some examples of some applications where you could use this technology?
Yeah, so we imagine a future where you just have this embedded in your clothing and you could communicate that way when when it's not convenient for your eyes or ears. Notice that this is phoneme based. Anybody can use. Notice that we didn't develop this only for people with sensory impairments. It's for anybody. So the idea is it just becomes your daily communication. Wouldn't that be cool?
Seems very intuitive because it's language-based, so everybody knows that, as you were saying. But there are other applications. In the past, we have created a glove and a cuff that is used in the operating room for doctors that don't have the sense of touch. And mind you, there is not language there like speech, but we developed a communication language that was translated when the signals in the operating room were about, reducing the cognitive load that was already super high in terms of visuals and audios that were going to the surgeon. And instead of doing that, translating that into a language that the surgeons could interpret. And by the way, they improved the performance. The accuracy of what they were doing was higher than using the normal audiovisual signals that they had in the room. So this is a language for speech, but we can certainly create other type of languages that people can learn.
Yeah, that's a really good point. So from information transmission point of view, even if you use the tactile sense to provide just redundant information, not necessarily new information. So like in, congruence with whatever visual and audio information, say the surgeon's receiving. And we have data that shows that information transmission increases when you do redundant coding. So it's really important to not only use it to create send new information, but also just to reinforce the information you're already sending. So we have now tested more than 100 participants, and they're naive participants in the sense that they've never been exposed to this system before. And here I'm showing one data plot of these 10 people, of 10 of the 100 participants. On the x-axis, we see the cumulative learning time in minutes. Now, we not only track performance, we track how long it takes to learn something because, speed matters in addition to how much you can acquire, right? So you're seeing that. And people, by the way, people come in for 10 to 20 minutes a day because it's so intense, you get fatigued after half an hour. So this is like a weeks long study, and people, they come back day in, day out. So notice the scale is from 0 to 500 minutes. That's less than 10 hours. I just want to call out. That's all the time we can afford in the lab with other people. So on the y-axis, we see the equivalent number of words learned. And this is calculated by multiplying percent correct score with vocabulary size. So at first, we introduce people to 24 words and then 48 words, and we eventually build up to a 500-word vocabulary after weeks of training and testing. So this red straight line represents a learning rate of 1 word per minute. Okay, so you can see 3 participants managed to not only learn those 500 words, but at a rate that's above 1 word per minute. And then the 3 more in the green elliptic shape, they are slightly lower. So 6 of them actually learned quite well. And then like any study you would, especially involving language learning and all that, there's a wide variety of performance. And the other 4 participants learned between 100 and 300 words in the end. So I just want to show you all these. This is all achievable. If you know how to do this, we have a lot more to say about how to design signals to facilitate very high information transmission. But I hope that I have given you enough evidence to say that touch can process a lot more information than just a click.
Talking about perception first, then we're going to see how that's been implemented in a platform level. And then sort of like Nesh is going to explain this sort of language that they have created for the Windows operating system. Nesh, then back to you.
Awesome. Thank you, Manuel. So, earlier I talked about, how do we get into this new era of input and enhance or reinforce the different interactions we're doing every day with our PCs, with haptic feedback, something that engages your sense of touch. And this is something that's been very, part of our life with phones. I think the most common one is when you do tap to pay, you kind of double tap your button and you're holding your phone there waiting for the vibration to tell you that you've completed the operation and that your payment is successful. So it's a similar principle, and now we're bringing that to the Windows and to the PC operating system. So Manuel, if you can go to the next slide, we have a video here that will capture this experience.
Experience our world through touch. It's instinctive, immediate, and tactile. Haptics brings these same experiences to Windows through sensory language built on subtle signals, precise responses, and feedback you don't just see, you feel. Clicks that move with your touch, actions that come through with clarity, and interactions that feel natural by guiding you without breaking focus. It's not just a tactile response, it's a connection, a more intuitive, more confident way to interact with your device. Now that's the power of haptics.
What we're doing is, traditionally input devices are one way. So you use your mouse or touchpad or touchscreen and you do something on your PC. But the feedback you get that your action was completed is always visual, like something happens. So what we're doing now is providing physical confirmation of different actions that you do to give you that confidence, that clarity that the action you did landed. So if you go to the next slide, Manuel. Right. So we've created the system that allows you to feel Windows, literally. So it's subtle contextual haptic feedback that creates more confident and delightful interactions. And we definitely have a way in which we are bringing this experience to life because, if done improperly, haptics can feel overwhelming. So if you go to the next slide. The reason we're doing this is to really create engaging experience and differentiate the experience that users get on Windows. We've done a lot of user research on this type of interaction paradigm, and what we found is that like I mentioned, it improves the clarity by providing subtle confirmation. It is delightful. So getting these subtle moments of feedback from your system really is delightful. It increases your connection to the device. It also just is delightful in a way that it's hard to describe unless you feel it. And finally, it becomes essential. So what we've known is really your brain becomes very familiar with this and even stops noticing it after a day or two. But really, when you go to a device and you go to a device that doesn't have this haptic feedback, something feels broken or missing. And so its absence is felt and its presence is really just feels very natural. And this is really how we're bringing, it's not like a one shot, this is everything you get. We're gradually rolling this out where we feel that it's most impactful. So things like snapping windows or dragging and dropping files is something that we've enabled at the Windows operating system level. And we've also partnered with many applications where this is most useful. So, our first party app is PowerPoint. We can all relate to editing a presentation and really having to squint and look at those red guides as they show up to make sure your image is aligned properly, right? So now you can just feel the things snap together with haptics. And whether you're using a touchpad or a mouse, it feels consistent. And this same principle can extend to other, primarily creative apps where there's a lot like video editing, photo editing, where there's a lot of precision, a lot of alignment. So we really partner with these applications to enable haptics at the application layer. So this next section here just talks a little bit about how we design this experience, not just the effects, but also its integration in the operating system. So we want to make sure that there's direct cause and effect between the input and the haptic. So we don't want to give feedback for notifications or things that were not triggered by a direct input event. Then if you go on the next slide, we have very specific guidelines on scenarios that where haptics should be used. So if you play the videos one by one from left to right, when you're trying to be precise, you're aligning things, or if you're colliding with the edge of the screen or hitting a boundary, finally, action zones, like dragging and dropping files, you hover over a very specific target, or things like detents, where you're stepping through different values of a slider. So we're going to be publishing guidelines on June 16th that outline how this experience was designed and how it should be used by the developers and designers to really minimize overstimulation and overuse and provide a good, curated, and subtle experience. And then finally, on the next slide, we have design consistency. So we want to make sure that developers use this basically consistently across their apps, so not to create confusion. So if you go to the final slide here, I think this is a question that some of you are asking, like, how do you make sure that these haptics get designed consistently and implemented by different hardware suppliers, right? So I think there's a question from Jorg. So this is a two-part question. So one is the actual design intent. So we have provided an hardware implementation guide to the manufacturers on the ideal like waveform design on the input side, on what we think the intent should be, like different like sharpness, frequency, envelopes, all of those details. But how they translate into your actual hardware is going to be very different depending on your system. And that's where measurement comes in. So we've partnered, closely with Haptics Industry Forum, which is an organization that Manuel and myself are both part of. And we're coming up with a measurement system that makes it consistent. So currently, like what people do is they'll put an actuator on the trackpad and just measure the unweighted acceleration, but that doesn't represent what a human actually feels. So what we're doing is designing this rig that mimics a human finger pressing down on the touchpad and then measuring the haptics at that point, and then defining some metrics that capture the characteristics of the signal and making sure they're consistent across different hardware manufacturers. So there's the design intent and then the actual measurement. So what we're doing with Haptics Industry Forum is defining a consistent measurement platform and measurement data pipeline so that whenever we compare signals, they're apples to apples. All right, that was my content.
At the end of the day, I think we went discussing already multiple layers of this system, but this is just to reiterate that when we are trying to create good haptic systems, it's not just simple as saying, I'm going to find an actuator that has the amazing bandwidth, but at the end of the day, that actuator is going to be implemented in a system that has a transmission, mechanical transmissions, has a control system, has software systems. And so we see this as a complex layer system that needs to be carefully tuned in order to achieve what we want. And starting from what does the haptic signal communicate? What is that we want to convey to the user? How do we capture that information and put it into a program? That the abstraction layer at the OS level, what Nesh already showed, but then going at the lower level, which is an embedded system. And we all know that to create haptic system, we need a specific latency, super important. Otherwise, the perception of creating something is lost. And more importantly, we try to create this in terms of signals, parameters, something that Nesh talked about as well. And more importantly, what we were discussing, these measurement systems, whether it is for a trackpad, a mouse, a glove, or a telerobotic system, we always want to implement systems and devices that capture physical information that are related to perceptual metrics in order to know that this has been implemented properly and that we can implement multiple times this and make sure that it's doing exactly the same thing that we have said that it's going to do. We have seen that from the beginning, Hong talked about this simple feedback, and we can move to a more complex and rich communication level on a horizontal line. That's what I'm trying to represent in this graph. And we can go from simple devices that have simple actuators, single actuator, to spatial haptics and devices that are wearables and more complex. I talked a little bit about that haptic heart device, which is for surgeons. Through the sense of touch, using a glove and a cuff, we can communicate a language that tells the surgeon, you reach your target, you are pressing too hard, you are cutting too hard, too soft, you are not yet there. So this type of languages that we develop is specific for specific situations that are super useful, that increase the performance of this in this task. But in the future, we're going to see something that is beyond that. We're already looking at teleoperation, the physical AI, like last point, is very hot and a topic that everybody's talking about. If these robots are feeling something and interacting with real systems, and a user is controlling or interacting with these robots, we obviously need to feel that in our hands. This is something that research and laboratories have played with in the past, but it's now coming slowly into the everyday devices, commercial enterprises, and it's certainly something that we need to look at for new types of haptic feedback implementations. So at the end of the day, haptics is not a novelty. It's one way physical systems can communicate physical meaning with the multiple devices. And with that, I just want to close up with 3 main takeaways from this webinar. The first one is that HMI, one of the interactions that we can provide to users is through haptics feedback, but this type of feedback is underused, and it needs to go beyond having a single actuator. And in order to do that, we should use perception-based design, something that Hong has proven to be true and useful. And the last one is that this type of systems can be implemented at the platform level. Nesh shows how they have done it at the operating system in Windows, but certainly it's true as well for other type of devices, whether they're wearables or chairs or something else that we are designing. It can be done. We can communicate more information to users. And with that, that concludes our presentations.